Discuss power and energy. Power is a unit of measurement in watts. It is the rate of electrical energy generation or consumption. And it's instantaneous. It's what the device is consuming or producing at that moment in time. So here we've got a light bulb. This is a 50-watt light bulb. So it is, when it's turned on, drawing 50 watts. It is using 50 watts of power. That's how much the consumption is at that moment of time when it's on. We can say the same thing for PV modules. A 350 watt module under standard test conditions will produce 350 watts of power. If the conditions vary, so if the irradiance goes below standard test conditions, that power rating will change, and we discussed this more in our PV 101 class. But under standard test conditions, it will produce the rated amount of power. Now, power is rated in watts, and we talked about this in an earlier section. 1,000 watts equal 1 kilowatt. 1,000 kilowatts equal a megawatt, which is also equivalent to 1,000,000 watts. And 1,000 megawatts equal a gigawatt, which would be 1,000,000 kilowatts or 1,000,000,000 watts. So it follows the metric scale there. We usually say 1,000 watts is a 1 kilowatt, 1,000 kilowatts is 1 megawatt, 1,000 megawatts is 1 gigawatt. We don't usually talk about millions of kilowatts or billions of watts. Now, watts is made up of volts times amps. So if we know the voltage and we know the current, we multiply the two and we will get the watts of our load or our generator. If we know one of the other ones, so for example here, if we know the watts and the amps, we can divide the two. We can divide watts by amps, and again, this is division, so we have to follow it in the right order. Watts divided by amps will give us our volts, or watts divided by volts will give us our amps. So if we know any two out of the three, we can figure out what the third one is by adjusting the formula. So let's take a look at an example. If we know what our volts are and our watts are, we can figure out what the amps are. So take this light bulb again. This is a 50-watt light bulb. We can see on the package, obviously it says 12 volts on the package, but most light bulbs are 120 volts. So let's just pretend this is a 120 volt light bulb, a standard light bulb that would go into a fixture in our homes in the United States, not this special RV marine light bulb that's operating at 12 volts. So if we know that this is a 50-watt light bulb, we assume that it's a 120 volt system. We divide 50 watts by 120 volts and we get 0.42 amps. So that's the current that this light bulb is going to draw at 120 volts. So we know what the power rating of this light bulb is, both in watts. We can figure out the current if we need to, if we know the volts. If we knew the current or amps rating, we could figure out the voltage of the light bulb as well. So we can do both of those calculations. There is a relationship between volts, amps, and watts. So if we have a 24 volt load and it's pulling 100 amps of current, it's going to consume 2,400 watts instantaneous power at any time that it's on. If the voltage is doubled, the current is going to be cut in half to keep the power at the same rating. So if we take that same load, change it to a 48 volt load, it's only going to draw 50 amps, half the amount of current for the same amount of power. If we go up to 120 volts, that would be 20 amps, so the current is even lower for the same amount of power. Same thing if we go up to 240, we've doubled it again, so we've doubled the voltage again. So we cut the current in half to get the same amount of power. Same thing going up to 480 volts. Now we're down to 5 amps. Note that on the right hand side we have the same amount of power in each of these equations, but as we increase the voltage we reduce the current to keep the power the same level. They are inversely proportional. So if one goes up, the other one is going to go down, and vice versa. Now, why does this matter? Well, the higher the voltage, the lower the current. The lower the current, and the higher the voltage, the lower the voltage drop. So the higher voltage systems tend to be more efficient than lower voltage systems, especially when we're going over long distances. Now, energy is simply power, watts, over time, hours, and that is measured in watt hours. We combine the two together. So if we take the watts of our appliance, our load, or our generating source and multiply it by the number of hours, or by an hour, we will get a watt hour rating. So that 2400 watts that we saw in the last slide, if that load was on for an hour, it would draw 2400 watt hours. If it was on for 200, it would draw 4800 watt hours. We can also convert that to kilowatt hours, which is the most common measurement for energy, and that would be 2.4 kilowatt hours or 4.8 kilowatt hours. This is a measure of the total work performed, and that can be attributed to either a load consumption or generator production. They both use energy as a unit of measurement. Here we have an example. We have a 50 watt light. It's going to be on for 3 hours. 50 watts for 1 hour is 50 watt hours. For the second hour, it's another 50 watt hours. And then the third hour, it's another 50 watt hours. So when we total that up, how much energy is going to be used for that 50 watt light for 3 hours? 150 watt hours, or 0.15 kilowatt hours. And just to give you a comparison measurement, the average household electricity in the United States is around 29 kilowatt hours per day. And again, kilowatt hours follow the same metric equivalent as the power rating watts do. So 1,000 watt hours equals 1 kilowatt hour. 1,000 kilowatt hours equals a megawatt hour, and 1,000 megawatt hours equal a gigawatt hour. So just to summarize, it's really important to know the difference between power and energy because they're used for different things. We need to make sure when we're answering questions or looking at situations that we are talking about apples to apples. Are we comparing power to power, or power to energy, or energy to energy? If we are doing a power calculation, we're not going to use watt hours because that's an energy unit of measurement. If we're doing an energy calculation, we're not going to use watts or kilowatts because that's a unit of power. They're very different when it comes into calculations, and they're used for sizing different pieces of equipment when we're working with PV systems. That's the end of our section on power and energy. In the next part, we are going to take what we've learned and use it in some real-world examples specific to the PV industry. So join me for that part when you are ready. Thank you.